In this video I am looking at noise in third overtone 10 MHz crystals. I am using many of them in parallel, as you may have seen in previous videos, and I have encountered problems with noise in some of the crystals. And now I am testing them one by one using this schematic. First an up transformation by a factor of 4, and then a small capacitor to couple to the crystal. And then an inductor through which I place DC bias for the FET. And then this is just a source follower, and it has a low impedance, so I put 47 ohms here and the capacitor to get about 50 ohms, a little bit more. But I'm not so interested in the flat noise floor far from the carrier, so a small mismatch here is uncritical. The reason for the up transformation is it is necessary to allow resonance, because I cannot put much capacitance on a single crystal to get the resonance frequency where I have my low noise oscillator at 13 Hz above 10 MHz. So up transformation and a small capacitor gives a hard coupling to the crystal, which means the Q is very low for a third overtone crystal. That means that since I know they have the same series resonance frequency, they should have the same inductance roughly at this fixed frequency. So I can test the different crystals without the need of tuning differently. I'm using the oven where there is place for 21 crystals. And in the previous video I used all of them in parallel and found there are noise problems. So now I can test them one by moving this white wire from crystal to crystal. I have a current probe here. The current through the crystal shows 355 millivolts with a probe 2 milliamps per millivolts. This means that the power in the crystal is about 400 microwatts for a 65 ohm crystal resistance. That is a factor 4 above what I think is normal maximum power for these type of crystals. But I have tried lower power and it doesn't improve, at least not 6 decibels or 10 decibels. Maybe at very low power levels, but that's not interesting. So I try at this high power to select if I can find many enough crystals that can work here. I can then happily use them at 100 microwatt and hope that they will last for a long time. So the peak current is 2.7 milliamps, which means about 1.9 milliamps RMS. Marker number 1 is at the frequency of my test oscillator, the Wenzel. And marker number 2 is at the peak of my filter, where the crystal is. And as you can see, it is very flat. It is within plus minus a couple of tenths of a dB, within plus minus 5 Hz from the Wenzel frequency. The total span here is 50 Hz. The input impedance is close to 50 ohms at the frequency of my oscillator, but it's highly inductive. And the inductance changes with frequency, of course. This gives a fairly high standing wave ratio. At the test frequency it is 4.9. I have measured the noise of all the 21 crystals in the oven, and they are very different. I found 6 ones that are good, and a couple of questionable and some really bad. So I step through the measurements. Really bad. Good. I have set this one as questionable because there is a little noise hump here. Bad, bad, good. And this is how it goes. This is one of the bad crystals, and it behaves like this when I start it. And here you can see the noise from 100 Hertz and down to 10 Hertz. And it goes fairly rapidly to collect the information on how bad it is. I want to measure the impedance of the good crystals in the oven at the correct temperature and at the frequency of my Wenzel oscillator. So I have calibrated my network analyzer to this end point of this wire, and I will solder it to the good crystals one by one and look at the impedance. Here is a typical result. I have 145 crystals. 65 of them are good and 55 are bad. And 25 are questionable. And from these, the good ones here, I will select 21 that span a fairly narrow frequency range, means they have nearly the same inductance. The reactive impedance goes from 941 ohms up to 1060 or 1070. So it is about a 10% variation of the inductance, means variation of the current. I have placed the 21 selected crystals in the thermostat oven, and I have restored the amplifier from the previous video, nerds113, which you see here. And it has the features of feedback to the drain of the source follower, making the drain voltage nearly the same as the gate voltage, to avoid the gate-to-drain capacitance variations due to noise currents through to the FETs. I have not yet fine-tuned the phase of that, which would be done with this trimmer inductor. But the performance is quite good, even so. This has been running for 33 hours now. I had to wait very long until I can see the noise from my selective amplifier with the 21 crystals. And you can see it here. The random fluctuations here means this is the noise of the test system. But here the curve is less noisy, so it means that at about 50 Hertz, the noise floor is at about minus 155 dBc per Hertz. The noise at 1 Hertz offset is at about minus 140 dBc per Hertz. And at 100 Hertz, it's below where I can do measurements with this system. And out here, it's just meaningless because the power of this signal is not adequate for measuring at these low levels. This is the measurement of the added noise from the selective amplifier. What will be the result when I make an oscillator out of it? I don't know. Maybe when there is feedback, also noise components will be amplified if they are close to the carrier. But I expect the noise at, let's say, 10 Hz offset to be in the order of minus 160 dBc per Hertz. Because at this separation, not very much will pass through the filter. Here is transmission through the box. Q is not particularly high, just below 800,000. I'm used to see slightly above 1 million. But I will leave it like this because I want to see what performance an oscillator could get. And then maybe I will improve the Q by changing some things around the filter. The phase shift through the box is 100 degrees. I have to add something to correct for that. I need 0 degrees phase shift. I have added a phase shifter here, shifts nearly 90 degrees. And then a buffer amplifier, the same as here, and it's connected in series with this one. And after that, an amplitude limiter, 2 FETs, no supply voltage, they are just switches to connect a 30 ohm resistor or whatever to ground to reduce the signal level here. And then the feedback output that goes to the input here. The oscillator has been running for about half an hour now. That's not enough time. I cannot see the noise yet, but it is below minus 126 dBc per Hertz at 1 Hertz offset, and below minus 155 at 10 Hertz. I will leave it overnight and see what happens tomorrow. The oscillator has been running for about 9 hours now. The result is not quite what I hoped for. I see minus 125 at 1 Hertz offset. But the noise is very low at 10 Hertz, and at 100 Hertz I cannot measure it. I suspected that the high noise I saw could be caused by some single event. So I restarted, and here is the result now after 20 hours, and it's significantly better. At 1 Hertz, I would say here, minus 133. This is a little bit odd, the curvature here. Perhaps this could be caused by infrasound. I have not sealed the box properly. And at 10 Hertz, it hasn't converged yet. You can see the circles here. On the other hand, I am below the specifications for the PN2060, so I'm not really sure I know what I'm doing here. I made a time-lapse recording so I could see whether there are any events that happen. So it looks like this. And it takes some time. I look at 1 Hertz and you can see it is very quickly coming to minus 133. I can stop playing and just step through the video. About here, when there are 200 averages here, I can see minus 133. And then it's stable. I can see the imaginary part showing up beneath here, showing me that this is certainly enough. So I don't have to run for such very long times. Maybe somewhere between here, 400 averages between 1 and 10 Hertz is enough at these levels. And through the entire time span, nothing bad happens. I suspected that the high noise I saw could be caused by some single event. So I restarted, and here is the result now after 20 hours, and it's significantly better. At 1 Hertz, I would say here, minus 133. This is a little bit odd, the curvature here. Perhaps this could be caused by infrasound. I have not sealed the box properly. And at 10 Hertz, it hasn't converged yet. You can see the circles here. On the other hand, I am below the specifications for the PN2060, so I'm not really sure I know what I'm doing here. I have disconnected feedback and made my multicrystal unit a selective amplifier again. And I'm now sending a signal into it from the Wenzel oscillator, and I have set the level to give the same signal levels inside the amplifier as I had when it was running as an oscillator. And here is the output from the feedback port. And I can compare it with what I had when looking at the main output, which was this. And as you can see, the feedback port is here, and the output is at least 6 decibels below. This noisiness means it has not converged, so it will become a little bit lower. How much? I don't know. When I compare the feedback output to the noise when it runs as an oscillator, I don't know exactly how to interpret this, but as an oscillator, the noise is probably minus 132 or something like that, while the noise on the feedback output is minus 136 probably. And the noise here is below the noise I see at the feedback output. Of course, it cannot pass through the filter, not when it is 50 Hertz away, or is it 20, 30, 40 or 50 Hertz away. At 3 Hertz separation, something like this, there is still some transmission, but the noise is significantly higher. Maybe one could think there is a small hump here, but it would take a week to get good statistics. This is more than 36 hours, and I don't want to wait any longer. One thing with the feedback output is the flat noise floor. Here it is elevated significantly from what I had on the other output, but this doesn't matter at all. It does not go through the filter. It stays at this level, and at the region where it passes through the filter, the noise level is so much higher, so the flat floor is completely of no effect. Here is the phase noise at the main output. I have just moved the cable from the feedback output, and I have changed the attenuators in the analyzing system because the level here is a little bit lower. But what I see now, when I compare, here is the feedback output, twice as the long time, it's 24,800 here, and here it is 1,269. These look very similar, means except of course here. So this means that something I changed has influenced both outputs. So maybe the feedback output and the amplitude limiter don't add specific noise. I can compare this measurement of the main output with the old measurement I have, which is like this. And it looks very different. You can see here. So something I have changed was not good. I did not make many changes. One is that I replaced this amplifier by this amplifier with a couple of attenuators to give it 7 decibels attenuation in front of it. That's to get a little bit more signal into the box. I have added this connection through the phase shifter and to the amplifier. So I can disconnect here to remove that. And the last change, I have tuned these two inductors for the voltage to become exactly the same on the gate and the drain of this transistor. But I know exactly how it was tuned because I tuned it originally with the network analyzer, so I can restore that also. And when I back all these changes, I should get back the very good performance I saw earlier. I start by putting back the original amplifier. I want to have the same level at the reference input of channel 1 and also the same level of the devices under test. As it happens, the signal level is almost identical. It differs by 0.1 decibel, so I shouldn't have changed the amplifier. What I think could be the problem is that the AMD amplifier might add amplitude noise, and amplitude noise might interact somehow to produce phase noise. So I will restart the AM2060 and wait and see if there is any change now. Using the AMC 147 to boost the Wenzel signal was obviously a bad idea. Now I have removed it and used the original amplifier, my own design. And what I had with the AMC is this. And what we see here, I think that is amplitude modulation from that amplifier, because the carrier is not absolutely centered in the filter. When running as an oscillator, the frequency was half an hertz off the center frequency. So this has become what I have now. And this is actually a little better than what I had before. The old result, which I thought was so good, is this. And you can see noise here. And this is with 2600 averages. Now I have 2300, and this noise has not converged yet. I start to see some noise here. But this is obviously weaker now. And I think that is because I tweaked those inductors, setting the drain and gate voltage the same for the source follower. And looking at the new measurement, I see the little circles everywhere telling me that it has not converged yet. So if I wait longer, this will go down. But I will not wait longer, because I will look at the feedback output, which is the important thing. How does that compare to the main output? Does the amplitude limiter or maybe the high impedance phase shifter contribute to noise in the interesting region here? That is more important. Already after 3 hours, I can see a significant difference between this new measurement and the old measurement on the feedback output, which is here. Here I have clear noise. Now I have only the statistical uncertainty of a too short measurement time. You can see the little circles everywhere. So it isn't really relevant to compare with this bad measurement. I should compare it with the recent measurement on the main output. So I compare with the main output, which was this, but this was not a very long time, so I should really look at the previous measurement with much longer measurement time. That is here, and this is about 10 times longer measurement time, and it comes here, and maybe this new will go down here or even below. This noise here should be visible if it were present. So it means that this noise hump has disappeared, or at least become weaker. I have been collecting average correlation spectra on the feedback output for 26 hours now. And if I compare it to the old measurement on the main output, which I have here, there are subtle differences here, for example. But I'm not sure this is really a difference. I see the circles here, but I see the circles here also on the old measurement. But this structure is not present anymore. But here it looks odd. This looks like actually a noise. I should smooth the curve, and then there is no difference. But down here it looks like the noise level is a little higher. And that is natural, because the noise floor here is significantly higher than on the main output. And I attribute this to the impedance of 250 ohms on the input due to the phase shifter. But this cannot pass through the filter. The bandwidth of the filter is plus minus 5 hertz, or a little more perhaps. And what happens here is important, but down here I don't think it matters. I have added a capacitor, 10 pF, to ground for the source followers, and also tuned this inductor, reduced it slightly to restore normal Q for the crystal. It looks like this. Q is now 1.012 million, and the gain has increased by slightly more than 1 decibel. I don't want higher gain, so I have removed this winding with 3 turns, like this. And that shifted the curve downwards by almost the correct amount, just 0.2 decibels too much perhaps. I have connected the network analyzer to this BNC connector and the blue wire, which is just in the air here. So it picks up a little bit of what happens inside the oscillator. And this is what I see. I have placed marker number 2 here on the center here. and marker 1 is on the peak here of the transmission. This means that the separation is about from here to here, 2 Hertz per division, so it is about half an Hertz, and that is close enough. The unit has been running as an oscillator for 17 hours now. I can compare it with the previous result when I used it as an oscillator. Here, slightly more time, 1400, and now I have 1200. I can try to compare here around 1 Hertz, something like this. And this looks a little bit higher noise. I think I have gained 1 decibel because the 20% increase in the loaded Q. But it's a bit uncertain because of the very long times I would need to get a smooth curve, and also it is below specifications for this unit, the PN2060. Anyway, there are differences up here. A significant improvement now. This is the old, and here is the current measurement. I think this is infrasound, and the box may be a little bit tighter now because I made it very tight when tightening the screws, holding the lid. I will end this video now, and then I will seal the box properly against infrasound. I will add a power amplifier to get enough power to see the noise floor here above room temperature. I guess it's about minus 194 or something like that. And that means I need a power level well above 100 milliwatts to lift this noise floor above room temperature so it can be easily measured. And I will also clean up the internal. I will show what it looks like now. The components of the amplitude limiter, transistors here and, well, some inductors and other stuff, are hanging in long wires, and that makes them sensitive to vibrations at fairly low frequencies. So I will clean this up and place a power amplifier here to boost up to a couple of 100 milliwatts or so.